Hello, my name is Michael Duda, and this lecture is the first of 3 lectures about how to run the MPAS model. So in this first part, we're going to look at creating initial conditions for the model, and then how to run a basic global simulation using those initial conditions. And when we say basic here, we're really referring to just a uniform resolution global simulation. In the second lecture, to follow this one, we're going to look at how to run variable resolution global simulations, and we're going to focus on a few other model runtime options. And then finally, in the third lecture, we're going to look at how to run limited area or regional simulations. But both parts 2 and 3 of this 3-part lecture series are essentially variations on this first part. So in that sense, it's very important that you first understand how to run a basic global simulation before looking at part 2 and part 3 of this 3-part series. So in the first part of this talk, we're going to look at how we can produce real data initial conditions. And when we say real data, we're referring to initial conditions that in principle represent the actual state of Earth's atmosphere at some point in time on a calendar. And this is in contrast to idealized initial conditions that we'll talk about a bit later in this lecture. So creating real data initial conditions typically happens in several different steps. And in this first step, we need to process or interpolate time invariant surface fields. And you'll often hear us refer to this as static file generation, and the word static here simply means that these are fields that are static or time invariant. And these would be fields like terrain height, or soil categories, or vegetation categories, or land sea mass, or things like that. Once we've interpolated these time invariant fields, we can generate a vertical grid using the terrain field, and then we can find some atmospheric analysis and from that interpolate atmospheric initial conditions. So a temperature field, a density field, a pressure field, a horizontal wind fields, and so on. And we can also interpolate land surface fields. And these would be things like soil moisture and soil temperature, fields that are used by the land surface scheme in MPAS-Atmosphere. And then lastly, although they're not exactly initial conditions, we'll talk about how we can interpolate sea surface temperatures and sea ice fractions and use those to periodically update the SST and sea ice fields in the model. And this can be helpful when running longer simulations because MPAS-Atmosphere as a standalone model doesn't contain a fully prognostic 3D ocean component. In the second part of the talk, we'll look at how we can take those real data initial conditions that we produced and use them to run a model simulation. And there's a few input files that we need to produce, and we'll go through those. And then in the final part of the talk, we'll go through the production of what we call idealized initial conditions. And these are initial conditions for particular cases with analytic initial conditions. And they don't generally correspond to anything that looks like the real Earth atmosphere at any point in time. Running these can be useful if you're testing the model, and particularly if you're developing, for example, new numerical schemes in the model and want to test the robustness of those schemes. And there are many details that are needed to fully appreciate some of the steps here, so there will be digressions along the way. So before we can produce initial conditions for the model, the first thing that we need to do is to obtain a horizontal mesh onto which we can horizontally interpolate these initial conditions. And this might come as a surprise if you're used to other modeling systems in which the horizontal mesh is something that's generated on the fly. In MPAS-Atmosphere at present, we need to download pre-computed or prepared meshes. And the way to do that is to go to the MPAS homepage and to firstly click on the MPAS-Atmosphere download link over on the left. And that will show you the pane that's shown here in the center. Once you get to this page, you'll then want to click on MPAS-Atmosphere meshes, and that will take you to a download page where you can download a selection of prepared meshes. When you get to the MPAS mesh download page, you'll see that there's a selection of quasi-uniform meshes, and if you scroll further down, you'll see that there's also some variable resolution meshes that you can download. You want to click on one of these links to download a mesh and put it into your working directory on your computing system. When you download the meshes, you'll notice that they have some interesting file names. So for example, if you downloaded a 120 kilometer quasi-uniform mesh, you might get a file that's called x1.40962.grid.nc. And there's a selection of other file names that you can see here on the screen. So as a new user of MPAS, it's a reasonable question to ask, how do we interpret these seemingly cryptic names? Well, essentially, the first part of the file name indicates refinement in the mesh. So x1 means a refinement by a factor of 1, in other words, no refinement. And x4, for example, means that the mesh refines by a factor of 4 from the coarsest part of the mesh to the finest part of the mesh. And a factor of 5 is indicated by x5, for example. The second part of the file names indicates the total number of cells in the mesh. So for example, the x1.40962 mesh has 40,962 cells in it. And generally, the more cells in a mesh, the higher the resolution. So when you click on one of the download links on the mesh download page, what you'll actually get is a tar file that contains not only the MPAS mesh itself, but also what we call mesh partition files or graph partition files. And we'll say a little bit more later about what's contained in these mesh partition files, but essentially they tell the model, if you're running with multiple processors or multiple MPI tasks, how do you divide up or partition the cells in the mesh among different processors in an equitable way? So inside of one of these tar files, for example, the x1.40962 download, you might get files that look like the following. So the file that's called grid.nc, this is a netcdf file that contains the actual grid or mesh itself. And then you get this graph.info file. This is a description of the mesh connectivity, which you can use to create your own mesh partition files. And then in turn, these graph.info.part.something are partitions of this mesh using this graph connectivity information. So for example, if we wanted to run the model using 2 MPI tasks on 2 processors, we would need this file called x1.40962.graph.info part.2, and so on for different numbers of processors. So now that you've downloaded an MPAS mesh, we're ready to try creating initial conditions and running a simulation. And if you think back to the lecture about how to compile MPAS, you might recall that there were 2 different cores or 2 different executables that we needed to compile. So the first of these is the init-atmosphere model program, which was created by compiling the init-atmosphere core. There's a lot of functionality that's wrapped up in this init-atmosphere model program. So this is the program that you can use firstly to handle all stages of pre-processing for real data initial conditions. This is also the program that handles the processing of SST and CIS update files. It's also the program that handles the generation of different idealized initial conditions. And lastly, this is a program that you can use to generate lateral boundary conditions to use in limited area or regional simulations. So through this program, once you've generated initial conditions, and when we talk about limited area simulations, we'll also see how to generate lateral boundary conditions, then you're ready to use the atmosphere model program, which was created by compiling the atmosphere core. So we can take those initial conditions with the atmosphere model program and integrate them forward in time to produce a model simulation. So we saw that the init-atmosphere model program embodied a lot of functionality. And you might wonder, how is it that one program manages to do so many different things? And the key idea here is that that single program is run using different combinations of options. So if you want to activate one of those bits of functionality that we talked about on the previous slide, you would use one combination of options. So the first and most important setting in what's called this init-atmosphere namelist file that we'll talk about in the next slide is the config init case specification. So this is an integer that tells the init-atmosphere program what sorts of initial conditions it's producing, for which initial case should it generate initial fields. So for example, a value of 2 would specify the creation of idealized baroclinic wave initial conditions. A value of 7 would specify the creation of some sort of real data initialization. And a value of 8 specifies the creation of SST and CIS updates, while a value of 9 would specify the creation of lateral boundary conditions. So for example, once we choose 7 to specify that we want to create real data initial conditions, we can then turn our attention to this other nameless group or nameless record called pre-proc stages or pre-processing stages. So as we said at the very beginning of this talk, there are several different steps to create real data initial conditions, and we can activate those different steps with these logical flags here. So for example, if we wanted to handle the static initialization, we would set config static interp to true. And if we wanted to create a vertical grid, we would set config vertical grid to true. And if we wanted to horizontally and vertically interpolate atmospheric initial conditions, we would set config met interp to true, and so on. And all of these options are documented in the user's guide. So we know that the init atmosphere program can be used to create our real data initial conditions, and we saw in the previous slide that there are various different combinations of options that can be specified to instruct this program to create exactly the initial conditions that we need. So as input, this program generally needs two text files that you have to edit. And the first of these is what's called a Fortran namelist, and that resides in a file called namelist.initAtmosphere. And inside of this file, as we saw in the previous slide, you can specify what sorts of initial conditions you want to produce with that config init case option. And secondly, we can select sub options. For example, we could say that we're creating real data initial conditions, but we only want to process the time invariant or static fields. All of these options get set in this namelist.initAtmosphere file, which is just a plain text file that you can edit with your editor of choice. The second file that we need to edit before running the init atmosphere model program is this file called streams.initAtmosphere. This is an XML file, even though we've chosen not to use a .xml suffix. So again, it's something that you can edit with your text editor of choice. And this is a file that allows us to specify which netcdf files will be read and written by the init atmosphere model program. So you can imagine, for example, that we might need to tell the init atmosphere model program where to find our netcdf mesh file that we downloaded, as we talked about a couple of slides back. That would be, for example, set in the streams.initAtmosphere file. So we know now that we need to edit this nameless.initAtmosphere program to specify all of the options that are needed by the init atmosphere model program to create real data initial conditions. And as we said back at the beginning of this talk, one of the first steps that we do to create real data initial conditions is to horizontally interpolate these time invariant or static terrestrial fields. And we already mentioned briefly what we mean by these fields, but it's helpful to take another look. So when we talk about static fields, we're talking about things like terrain elevation, or the dominant land cover category, or the dominant soil category, or things that are used by various parameterizations in the model, like the subgrid scale terrain variance that's used by a gravity wave drag scheme. There is also climatological fields given for every month of the year. And because these are climatologies, they don't generally change in time. We use the same monthly climatological vegetation fraction and surface albedo for the month of January, regardless of which January it is that you're running a simulation. So because these are in principle fields that don't need to change in time depending on your atmospheric initial conditions, this means that you really only need to run the static processing step once for a given MPAS mesh, and those time invariant fields can be reused for many different simulations on that mesh. So the data sets that provide global terrain elevation and land use categories and soil categories and other static fields are actually borrowed from a different modeling system called the Weather Research and Forecasting Model, or WRF model. So after you download and compile the MPAS model, one of the next things that you might want to do is to go to the WRF model download page. And I don't know whether you can see the URL here in this web browser screenshot, but if you go to that page, you can download these geographical data sets, and you'll unpack them somewhere on your file system, and we'll see in the nameless.initAtmosphere file how you can specify the path to these data sets. So in summary, these are data sets that don't come with the code because they're several tens of gigabytes in size, but you need to download them separately before you can run a real data simulation. So if we assume that you've downloaded the MPAS model source code and you've compiled the init-atmosphere core, and furthermore that you've downloaded an MPAS mesh from the MPAS mesh download page, and you've downloaded these geographical data sets from the WRF geographical dataset download page, then essentially running the init-atmosphere program requires you to prepare these two input files that we talked about a few slides back. So firstly, you'll need to edit this nameless.init-atmosphere file, and a default version of this file will be created for you when you compile the init-atmosphere model program. And you'll need to make appropriate settings there, which we'll talk about in a couple of slides. And then secondly, you'll need to edit this streams.init-atmosphere file. And like the nameless file, a default streams file is created for you when you compile the code. So after you've made changes to those two files, you're ready to run the init atmosphere model program. And assuming all of your settings are correct, the result should be another netcdf file with a file name that you've specified in the streams file. So for example, if we were doing a simulation on the 40962 cell mesh, this quasi-uniform mesh is about 120 kilometer horizontal grid spacing, we might get an output file that's called x1.40962.static.nc. And inside of this netcdf file, we should find all of the fields, the static fields that we talked about a couple of slides back. So for example, here we're looking at a contour of what I believe is probably the vegetation category. Additionally, the init atmosphere model program will write out a log file, and this will tell you all of the steps that the program has taken in order to interpolate these fields, and it's also a good place to look if you suspect that the program hasn't run correctly. We've made quite a bit of effort to make sure that we write out useful error messages, so it really is worth taking a look at the log file. So here on this slide, what we're looking at are the key settings that you need to provide in the nameless.initAtmosphere file when you want to process these static or time invariant terrestrial fields. So the first thing that you want to do is to set config init case to 7. If you recall from a few slides back, 7 means we're creating real data initial conditions. And down in this pre-processing stages name list, you want to set static interp to true. There's also this option native GWD static, which causes the program to process subgrid scale orographic fields that are used by the gravity wave drag scheme in the model. And like the terrain field, these subgrid scale terrain statistics don't change in time. So typically when we process static fields, at the same time we also process these gravity wave drag static fields. And that's it. We'll set all of these other pre-processing stages to false. Now, when we're processing static fields, there are a few additional settings that we need to provide in this data sources namelist group. So this config geog data path option tells the init atmosphere model program where it can find these geographical data sets. So after you've downloaded these data sets from the WRF model download page and put them somewhere on your file system, you'll need to specify that root directory here. There's a couple of different sources of land use and topography data that are available in this geographical dataset download. So you can choose between, for example, MODIS or USGS land cover data, GMTED, or an older GTOPO 30 terrain dataset, and a few different options for climatological vegetation fraction albedo and snow albedo. But generally, the default options for most of these are what we would recommend. So really the only thing that you need to change is the path of the geographical data, because that's of course specific to your system. In the streams.initAtmosphere file, there are really just two things that you need to change. So the first thing that you want to do is to find this input stream that's called input. And inside of that XML tag, you want to find the attribute called filename template. This specifies the name of the input file, the netcdf mesh input file that will be read by the init atmosphere model program when it's processing static fields. So this should be set to the name of the grid file that you downloaded from the mesh download page. The second thing you want to do is to find the output stream and to set the file name template for the output. And as we suggested a couple of slides back, a reasonable name is the same prefix as your grid file plus static.nc to indicate to you and other users that this is a file that contains static fields only, not full initial conditions. So after you've edited the namelist file and streams file, as described in the previous slide, you're then ready to run the init atmosphere model program. And as we saw, the result should be a netcdf file with a file name of your choosing that contains interpolated terrain, land use categories, soil categories, etc. It's also important to point out that for the static processing only, you have to run the init atmosphere model program with just a single processor. So on most systems, this means that if you're willing to run the program interactively, you can just say /init atmosphere model and it will run. The static processing takes about 45 minutes, but the result should be this static.nc file. It's also worth pointing out that the input mesh at this stage is a unit radius sphere, and the output of this first static pre-processing step should be an SCVT mesh with a sphere radius of 6,000 371.229 kilometers. And as we mentioned a couple of slides back, the init-atmosphere model program also writes out a log called log.init-atmosphere.0000.out. The 0000 is processor 0's ID, and as we said, the static processing has to be done with just a single MPI task, so you get a single log file for processor 0. And as we said, it is important to look through the log, and for the static preprocessing step, you should see a few things that are indicated here. So you might see a message that says enter subroutine init ATM static, and then it tells you that it's processing a terrain data set, and a land use data set, and a soil category data set, and a few others. And then if you've activated the processing of gravity wave drag static fields, you should also see a message somewhere in the log file that says computing GWDO static fields. And then at the very end of the log file, you'll always get a summary that tells you how many total messages, warning messages, error messages, and critical error messages were generated in the execution of the program. The important thing to note is that we have 0 errors and 0 critical errors. So that's an indication that the program successfully ran. So we've just seen how we can run the init-atmosphere model program to create this static netcdf file that has all of these time-invariant terrestrial fields. And that, as we said, takes about 45 minutes, but because these fields don't change in time, you only need to do that a single time for a given mesh. And now what we're going to do is turn our attention to the interpolation of atmospheric and land surface initial conditions. So once we have a terrain field, we can then generate a terrain-following vertical coordinate surface, or a set of terrain-following vertical coordinate surfaces. And that gives us a 3-dimensional grid to which we can interpolate our atmospheric initial conditions. So we need to digress for just a minute here and talk about where we get these atmospheric initial conditions, the data sets that provide these initial conditions. So you might be aware that there are various sources of atmospheric analyses or reanalyses out there, and you might even imagine that it's possible to take global output from an operational forecasting model that's run, for example, by the US National Centers for Environmental Prediction or the European Center for Medium Range Weather Forecasting, and to take that set of atmospheric fields and use those as your initial conditions. It turns out that the init-atmosphere model program expects whatever source of atmospheric initial conditions that you want to use to be in a specific file format. And this is another place where we've borrowed something from the WRF modeling system. So the format of these atmospheric analyses is the so-called intermediate format. So before you can create atmospheric real data initial conditions, you need to use the WRF preprocessing system to take some atmospheric data set and to preprocess it and turn it into what we call an intermediate file. So we're not going to cover that process in this tutorial. There's already material that's linked here at the bottom of the slide that will guide you through the process of running a program called ungrib, that's part of the WRF preprocessing system, to take data sets in what's called grib format and to turn them into this intermediate file format that's readable by the init-atmosphere model program. So, assuming that we now have some intermediate file that contains 3-dimensional atmospheric fields like temperature and horizontal winds and humidity and pressure and temperature, and assuming that we've already produced this static netcdf file that has terrain and land use categories and a few other time-invariant terrestrial fields, we can then go through and make some changes to a nameless.init-atmosphere file again. And here you can already anticipate that what we're going to need to do is to tell the init-atmosphere model program that we want to interpolate atmospheric fields. And then we're also going to need to make some changes in our streams.init-atmosphere file to tell the init-atmosphere model program the name of our static field that will be read as input and the name of the netcdf file that we want to write as output. And this output file now will contain 3-dimensional atmospheric fields that will serve as our initial conditions for the model. So after we run the init-atmosphere model program, the first thing that we should get out is this file, again another netcdf file whose name will be specified in the streams.init-atmosphere file, and this will serve as the initial conditions for our global MPAS simulation. And secondly, we should expect to get a log file. And again, just like when processing the static fields, it will be important to look through this log file and verify that the processing happened as expected and that there were no errors. So inside the nameless.initAtmosphere file, we've highlighted the key settings here. So we still want to produce real data initial conditions, so we'll keep config init case set to 7. But now, because we're processing time varying fields, we need to specify the valid time of the fields in this intermediate file that contains atmospheric state. So we'll set that with this config start time option. In this case, we're saying that we want to produce initial conditions that are valid at 2014 September 10th at 0 UTC. And all of the date time strings that are used in MPAS are UTC time. Now, because we're doing three-dimensional processing, or processing of three-dimensional fields, we need to specify some things about the vertical size of our mesh, or the vertical extent of our mesh. So we can do that in this dimensions section of the nameless file. So we can set the number of vertical levels. This will be actually the number of vertical layers that are used in our model three-dimensional initial conditions. We'll need to specify how many soil layers to use. And it turns out this always needs to be set to 4 because the land surface scheme in MPAS uses 4 soil layers. And then we also need to specify what's called the number of first guess levels. This is the number of levels that are in our input file that provides our atmospheric first guess or initial conditions. So this should be at least as big as the number of layers in our intermediate file. And then lastly, we need to specify the number of first guess or FG soil levels. And this is typically 4 as well, the same number as are used in the model itself. Now, we also need to tell the init-atmosphere model program where to find this intermediate file. And we do that with this config met prefix string here. So this is set to the string of our intermediate file, and you can optionally specify relative or absolute path information here. And this string is suffixed with a colon and then this timestamp here. So this means that we should have in our run directory an intermediate file that's called gfs:2014-091000. And I think usually the minutes and seconds are omitted. So that's it. We're telling the init-atmosphere model program how to build the vertical grid in our model and when our initial conditions are going to be valid. There are a few other nameless options that we need to set that pertain to the vertical grid, and those go in this vertical grid nameless record. So config ztop is the top height of our model. So we're saying that we want the highest layer interface in our model to be at 30 kilometers above mean sea level. There are some parameters that control the smoothing of the vertical coordinate surfaces. So we can set the number of smoothing passes for terrain, whether to smooth the coordinate surfaces themselves, the minimum delta zeta value, and the number of smoothing passes, the maximum number of smoothing passes that can be applied to each coordinate surface. So all of these options generally, I would say if you're starting out with a model, just keep them set as is. But as you become a more advanced user, you might want to, for example, use a higher or lower model top, and you might want to more aggressively smooth terrain as you get to higher resolutions. But again, as a starting point, keeping all of these default options in the vertical grid nameless group is a reasonable thing to do. And then we also return to this pre-processing stages nameless group. And now we need to set static interp to false because we've already done that processing. And we need to set GWD static to false. Again, we've already done that processing. Instead, what we want to do is to use the terrain field that was provided by our static file, plus all of these vertical grid settings to generate a vertical grid. And secondly, we also want to interpolate meteorological fields from this intermediate file. And then typically we also set frac sea ice to true as well when we produce initial conditions. And finally, inside the streams file, the streams.initAtmosphere file, there are just 2 settings that we need to make. As we did when we process static fields, we need to set the name of the input netcdf file in the input stream. And here our input file is going to be the static file that we produced in the previous step. And then as output, we want to say that our output file is going to be named x1.40962.init.nc. Again, our convention is usually that the same prefix is used, so that if we have multiple initial conditions in our working directory, we can distinguish them. But you could, in principle, choose any name you want here. So you could call this init 2014-09-10.init.nc if you wanted. The choice is completely up to you. So if we've run the init-atmosphere program, as we saw in the cartoon a few slides back, we should get an init.nc netcdf file as output. And what this netcdf file actually contains are all of the fields that were contained in our static file, plus now a vertical grid based on the settings that we provided in our vertical grid namelist group, and then interpolated atmospheric initial conditions. So for the atmosphere model, we actually need potential temperature, normal component of winds on cell faces, and a vertical velocity on vertical cell faces, water vapor mixing ratio, and then some land surface fields like soil moisture and soil temperature. And as before, it's always worth checking the log file to make sure that there are no error messages. So when we create initial conditions, you might want to look through the log file and verify, for example, that we have a message that says setting up vertical levels. And you also might want to check the maximum terrain. So of course we know that, for example, the Himalayas go much higher than 5,400 meters because we're working with a very coarse model mesh. The resolution of the topography is low enough that we're not actually seeing the highest peaks and mountain ranges. So it's reasonable just to make sure that this is, for example, a non-zero value. And then you'll see these messages that say interpolating, 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 interpolating. These are the messages that indicate that the init-atmosphere model has interpolated in 3 dimensions: a temperature, zonal and meridional components of winds, relative humidity, and geopotential height. So at this point, we have initial conditions which are completely sufficient to run a global model simulation. And being a global simulation, we don't need lateral boundary conditions. But as we said at the outset of this talk, for longer simulations, because the MPAS-Atmosphere model doesn't contain a 3D prognostic ocean, we might want to provide some means of periodically updating the sea surface temperatures that are seen by our simulation, as well as the sea ice fractions. And that can be done once again by running the init-atmosphere program with a different combination of settings in the namelist file. So schematically, when we set out to produce SST and sea ice update files, again, we're going to be running the init-atmosphere model program. And as in the previous 2 steps, we're going to make some changes in the namelist file and also in the streams file. And before running the init-atmosphere model program, we do need to provide some mesh that has a land sea mask. And this could either be our static file, because we're assuming that the land sea mask doesn't change in time, or this could be the initial conditions file that we produced in the previous step. Either of those files would work. And we also need files that provide SST and sea ice analyses. And as with the atmospheric initial conditions, those files come in this WPS or WRF preprocessing system intermediate format. So in the same way that you produced atmospheric initial conditions in the intermediate format, you would produce a series of files that contained SST analyses in this intermediate format, again using the WRF preprocessing system. So the idea then is that we'll once again run the init-atmosphere model program, and based on the description of the input and output file names in our streams.init-atmosphere file, we will now get out a file that's conventionally called surfaceupdate.nc, and optionally, by convention, we use this same prefix as for our static file and initial conditions file. But again, this is completely optional. And as with every other execution of the init-atmosphere model program, we get a log file. So when we set out to edit our namelist file to produce an SST and sea ice update file, we've summarized the key settings here. So if you think a few slides back, we had a separate initialization case to produce SST update files, and that number happens to be 8. So we're going to ensure that init case is set to 8. And now, because we're processing a range of times, because we're periodically throughout the course of a simulation updating the SST field, we need to specify the starting time, which is typically the same as the time at which we're starting our model simulation, although in principle it could be before the start time of the model simulation. And we need the stopping time. And this is typically the same as the stopping time that we intend to use for our model simulation, but it could be later. So for example, if you wanted to process an entire month of sea surface temperatures, but we only wanted to run a simulation for a subset of that month, that would be completely okay. Now inside this data sources nameless group, we need to specify the prefix of the intermediate files that contain SST and sea ice fields, and that's given by this surface prefix variable here. And we also need to provide this first guess interval. So this is the interval in seconds between intermediate files that provide us these SST and sea ice fields. So 86,400 seconds is 1 day. So we're saying that every day from the 10th through the 20th of September 2014, we have an SST analysis. And then down in the preproc stages nameless group, we'll set input SST to true and fractional sea ice to true. And that's it. All other stages are set to false. And inside our streams file, there are just a couple of changes that we need to make. So we'll ensure that the input stream is set to the name of a file that contains a land sea mask, because the SSTs are generally only valid over water points. So if we had already set the input file name to, for example, the name of our static file when we created initial conditions, we could keep that setting. And then we need to also find the stream called surface, and we need to set again the name of our surface update file to be created. And as we said, you can choose any name you want here, but by convention it's called, the same prefix as the static file plus surfaceupdate.nc. And then we also need to set the output interval for this stream. And generally this is set to the same interval at which we have SST analyses. So because in our name list in this example, we said that we have SST fields every 86,400 seconds, that's going to be the interval at which we're going to write out fields to this surface update stream. And as before, when we run the init atmosphere model program, we get a log file, and this time we should see a bunch of messages that indicate that we're processing SST intermediate files. So we said that we had 1 file per day from the 10th through the 20th of September, and indeed what we see here is processing file SST 2014-09-10, 11, 12, 13, and so on. And as before, the critical thing is to check down at the bottom in the summary here and ensure that there are no error messages and certainly no critical error messages. So now that we've produced initial conditions and optionally an SST and CS update file to be used in our simulation, we're ready to run our first MPAS simulation. But first we need to digress a bit and talk again about these mesh partition files. While creating initial conditions is something that can be usually feasibly done with a single processor, running the model is a much more computationally demanding application. And so almost invariably, you'll want to use multiple processors when you run a model simulation of any reasonable resolution. And so we mentioned earlier that we need these mesh partition files that tell the model how to distribute the cells in the mesh among the different processors that are cooperating to do this model integration in parallel. And in general, we need to use a program called MPAS to create these mesh partition files. The idea is that we can feed information about all of the locations and connectivity of the cells in the mesh to the MPAS program, and it generates a partitioning. And we usually aim to have contiguous partitions in space. So the set of cells that I'm highlighting here with the cursor might indicate the cells that are assigned to processor 0 in our mesh, and here might be the set of cells that are assigned to processor 1 and processor 2, and so on. However, as we mentioned earlier, many of the meshes that you download from the MPAS mesh download page come with several different pre-computed partition files. So in a lot of cases, as long as you want to use a number of processors that's equal to the number of partitions in one of the existing partition files, you don't actually need to run MPAS yourself. So for example, when you download the 120 kilometer mesh, you'll get the following set of files that we saw earlier in this talk. So you'll get a file called x1.40962.grid.nc, and this is the netcdf mesh itself. Again, this is a unit sphere mesh, which we can then inflate and interpolate terrain and land use and so on onto, and continue to produce initial conditions. We also get this file called x1.40962.graph.info. This is the mesh connectivity information, so it's a connectivity graph of the cells in the mesh. And if you were to produce your own partition file using this MPAS program, which you'll have to install yourself, this is the file that you would need to provide to MPAS. But these .part.something files are pre-computed partitions that we've provided for you. So, for example, if you wanted to run the simulation using 16 processors, you would need to ensure that the x1.40962.graph.info.part.16 file was in your run directory. So let's assume now that we have a mesh partition file as well as initial conditions in our working directory. It's worth pointing out that the same atmosphere model executable can be used for any sort of simulation, whether it's real data or idealized. The model doesn't really care the source of its initial conditions. All it cares about is that it has all of the prognostic fields in 3 dimensions that are needed to run a model simulation. So this means things, again, like potential temperature and density and horizontal winds and vertical winds and water vapor mixing ratio and a few other fields. So given initial conditions, all that's needed to run a model simulation are the following. So firstly, we need to edit our nameless.atmosphere file, and there's just a few key parameters that we need to set generally. And at least as a starting point, you can use most of the default settings in this nameless file. So we need to set the model time step that's used in the time integration of the model. We need to set a few mixing and damping parameters, and then you may want to choose different physics options, different parameterizations of physical processes. So most of these things are covered in separate talks. So there's another talk about the model dynamics, and there's another talk about model physics. So these are all set in the model nameless file. The next thing that you'll need to do is to edit the streams.atmosphere file. And notice that when we ran the init-atmosphere model program, the name of the streams and nameless files were nameless.init-atmosphere and streams.init-atmosphere. And now when we run the atmosphere model program, these are called nameless.atmosphere and nameless.streams.atmosphere. So anyway, we need to edit the streams.atmosphere file to specify the name of the initial conditions file that we prepared, as we described in the earlier parts of this talk. And if you're doing, for example, SST updates, you might want to set the interval at which those SST updates are to be read. And you might also want to set the frequency of the model state that's written out. We typically call that model history, even though this might be for a simulation that actually predicts out into the future. And then lastly, as we just talked about in the previous slide, you'll need to make sure before running the model in parallel that you have the proper mesh partition file in your run directory as well. And part of this file name of this partition file is specified in your nameless file. So in general, the model can't know that the file name is x1.40962.graph.info. You need to tell it that in your nameless file. And then once we've got all of these files present in our run directory, we can launch the atmosphere model program, perhaps in parallel, perhaps by submitting it to a queuing system on a computing cluster. And that runs our model simulation. And the idea is that being a global simulation, once we have initial conditions, the model can, in principle, run as far into the future as we like. Of course, the resemblance of that simulation to reality starts to diverge, but that's the idea. And so before running the model, we said in the previous slide that there were a few nameless options that had to be set correctly. And so it's worth highlighting those again here, because if these values aren't set correctly, the model will either fail immediately or it might fail after a certain amount of time due to numerical instabilities. So the first of these options that needs to be set correctly is an option called config start time. And this is the starting time of the simulation. And as you might guess, this needs to be set to the same time as the valid time of your initial conditions. The second option that you will need to set is config dt, or delta t. So this is the model time step given in seconds. And so a reasonable way to choose a value here is to take the minimum horizontal grid distance in your model domain in kilometers, multiply it by about 5 or 6, and then round down to the nearest number that evenly divides your model output interval. So for example, for the 120 kilometer mesh, we might choose a model time step of 720 seconds. So that's 6 times the model horizontal grid distance, and it also conveniently evenly divides 3,600 seconds. So if we had an hourly output interval, that would all work out nicely. And then lastly, another option that you shouldn't forget to set is the one called config len disp. So this is the length scale that's used for explicit horizontal mixing in the model. And generally, you want to set this to the minimum horizontal grid distance in meters in your mesh. So for the 120 kilometer mesh, you would set this to 120,000. In the second part of this series of talks on how to run the model, when we talk about variable resolution, we'll see how to set this appropriately for variable resolution meshes. But for global quasi-uniform simulations, this is just the horizontal resolution of your mesh. And then besides these options, you'll just want to make sure that you have appropriately set, as we said in the previous slide, the name of your initial conditions file in the streams.atmosphere file. So as you run the model, just like with the init-atmosphere model program, the atmosphere model program produces its own log file, and this is called log.atmosphere.0000.out. Again, the 0000 is just the MPI task ID, and by default, only MPI task 0 writes out a log file. If you were running on 1024 processors, you really wouldn't want 1024 log files that all had more or less identical information. So only in case of an error do other processors write out a log error file. So as the model's running, you can, for example, tail this file to watch the progress of the model as it's integrating. And what we've shown down here in this box is an example of some of the output that you'll see in the log file for a single model time step. So each of these blocks of output that shows up says begin time step and then a timestamp. So this is the current time in the model simulation, and this is the time that will be advanced by delta t seconds in this time step. Then there's some information about which physics schemes will be activated in this time step. And these are typically schemes that aren't necessarily called every time step. For example, shortwave radiation and long-wave radiation are typically called every 30 minutes or 15 minutes or 10 minutes in model simulation time. So this tells you whether those schemes are active in this time step. And then you get a quick summary of the min and max horizontal and vertical velocities at the end of that time step. So at the end of this time step, the min and max vertical velocities, which are identified by W, were minus 0.44 meters per second and positive 1 meters per second. And the min and max of the normal component of the horizontal velocity was about plus or minus 90 meters per second, which is a physically reasonable value. So these values are nice. As you're watching these values tick by in the log file, you can start to sense model instabilities as these values grow to physically unreasonable values. And that's usually a signal that you might need to change some settings in your name list. And then lastly, you get the wall clock time that it took to take this integration step. And this is really nice because it allows you to estimate about how long a simulation is going to take. So if we knew that each of our time steps advanced the model state by, say, 600 seconds, so in our name list we had set config dt equals 600, and we know that simulating 600 seconds took only a third of a second, that means that we're simulating about 1,800 times real time. 600 seconds and a third of a second is about 1,800 seconds per real-time second. So you can find the total length of your simulation, divide that by 1,800 seconds, and that's about how long in wall clock time you can expect it to take to run the simulation. And then, as with the init-atmosphere program, inside the log file, when the atmosphere model finishes, you'll just want to make sure that there were no error messages. And in this case, you can see that we have one critical error message. So this is our cue to go back and look through the log file and search for the word error with a capital E. And in this case, it's a silly error. It says critical error could not open input file x1.40926.static.nc to read mesh fields. And then it says, it's quitting. And we can think about this for a second and say, what's going on? Why can't it read this file? In this case, it happens to be a typographical error. I meant to type 40962, but I typed 40926. But you can imagine that there will be other similar error messages that indicate to you what might have gone wrong or why the model might have stopped. So in the last part of this talk, we're ready to discuss how we can create idealized initial conditions for the model. So if you're familiar with the process of creating real data initial conditions for the model, it turns out that creating idealized initial conditions is actually much, much easier than creating real data initial conditions. So there's no need for external data sets or multiple pre-processing steps because all of the model fields that are used in the initial conditions are prescribed by formulas. And essentially all that we need to do, besides providing a mesh on which we want to generate our initial conditions, is to choose the appropriate initialization case in our nameless.init-atmosphere file. And this is an ideal time to introduce the MPAS-Atmosphere user's guide. So you can download a PDF copy of this user's guide from the MPAS-Atmosphere model download page. And if you go to Appendix A in the user's guide, you'll find a description of all of the nameless options that are possible in the init-atmosphere model namelist. So in Appendix A, you'll see that there's a section that describes the config init case namelist option. And here we have a listing of all of those initialization cases. And you remember from earlier parts of this talk that initialization case 7 specified the creation of real data initial conditions, and initial case 8 specified the generation of an SST and CIS update file. And these other cases 1 through 6 correspond to different idealized initial conditions that we can generate simply by setting config init case to one of those values and providing an input base mesh. So some of these idealized cases require certain meshes that are not available on the regular mesh download page. For example, the squall line or supercell simulations require doubly periodic meshes that are defined with perfect hexagons on a Cartesian plane. So in most cases, I would say your best option is actually to download a prepared run directory for these idealized cases. And we'll see in just a couple of slides where you can download these prepared run directories. But essentially, after unpacking the tar file that you download, all that you need to do is to symbolically link in the init atmosphere model and atmosphere model programs into that run directory, and then just follow a couple of steps in the README that comes with that prepared case. So you can download these idealized prepared input directories by going again to the main MPAS model webpage, and on the left, once again clicking on the MPAS-Atmosphere download. That will take you to the frame that's shown here in the center of the screen. And rather than clicking on the mesh download, what you want to do is to scroll down a little bit and click on configurations for idealized test cases. That will take you to the following page, and you can see here that there are several different downloads for a supercell, which can also be used for a squall line simulation, a two-dimensional mountain wave case, and some idealized cases on the sphere, namely the Jovanovski and Williamson baroclinic wave family of cases. So you can download one of these again, unpack it, symbolically link in your init atmosphere and atmosphere model executables, and follow the README, and that's all there is to it.